shear flow at point C. So to find the shear flow at point C, this is the area that you take. So I will section it this way. Okay. So this is one area, and this is the other area. Okay. So the shear flow is dependent on the area of coverage, as you can see over here. Okay. Right. The next thing is the most important thing is constructing shear flow, the Q. Okay. How to draw the Q is critical. Okay. Later on, if time permits, we do a member that is made of different section. Okay, this is still required if we have the time. Okay, right. So now you have to, you know how to design the shear flow. The next thing I'm going to show you, okay, the next thing I'm going to show you is the difference. Let me zoom out so you can see better. The next thing we're going to see is the difference and similarity between thin wall and non-thin wall analysis. Okay, I want you to see the difference. Okay, and similarity. There are differences. There are also what? Similarities. Okay, so let's consider box beam first. Okay, let's consider box beam. So I'm going to again copy the image of the box beam. Okay. So on the left hand side is our thin wall. Okay, thin wall. And then on our right hand side is our non-thin wall. So I'll construct a non-thin wall. Okay, it's not. So now let's look at non-thin wall first. Okay, let's look at non-thin wall just to recap non-thin wall. Okay.
So just one quick question, if you don't mind.
Yes. Yes.
Uh, when we consider the section is thin wall or not, like until what thickness? So like I see the other one is also has a thickness, but we are considering non-thin wall, right? So when we would know that we are that this one is thin wall or not?
Good. Good. That's a very good question. So the question asked is when is it a thin wall and when is it a non-thin wall? For this course, I will tell you when it's a thin wall and when it's not a thin wall. In reality, you have to check. How do you check? Okay. If you're not sure, you calculate both based on both non-thin wall and thin wall analysis, and you will quote the higher value. Does that make sense?
Yes, sir. Yes, sir.
Okay. But for this course, okay, because you are learning the foundation, the fundamentals, I will tell you when is a thin wall and when is it non-thin wall analysis. Okay. Right. So let's say now we want to look at point A. Okay. And now over here is also our point A. Okay. So the first, let's look at non-thin wall first. Okay. And then I'm going to sketch our centroid. Okay, I'm going to sketch our centroid. So the area of consideration, right, for this case, the area of consideration, if you want to find the shear stress at point A, the area of consideration is, this is the area. Okay, this is the area. Okay, this is the area. So the distance from here to here, this is your small y, and the distance from here up to here, okay, which is your centroid of the area of interest, this is your y bar. Okay? And the thickness that we take is this thickness. Okay? This is the thickness. Okay? Now, the formula that we use are still the same, right? I'll write down the formula. So V is, not V, come on, Eugene, seriously. So Vy is still coming down here, right? So if we were to comply the transformation, that the vertical is your Y, the horizontal is your Z, okay? So the shear stress is equal to Vy over Izz, first moment of area QZ, and T. Okay, so the thickness is basically the width. Okay, so that is on non-thin wall analysis, right? Now, let's look at thin wall analysis. Okay, so for thin wall analysis, if point A is your point of interest, the area that you have to take is now look like this now. Okay, so that is the area of interest. And the thickness is this thickness. Okay, so first thing, what you see, the difference is for thin wall analysis, okay, the thickness is perpendicular to the shear flow, vector. Q. Okay, so you can see that the shear flow is running horizontally. Right? The thickness is perpendicular to the what? Shear flow direction. This is a big difference. Okay, there's a huge difference over here. And because if you look at point small a, right, from the terminal, the Q splits into two, right? You have Q going towards the left. You have the other Q going towards the what? The right. Okay. So the shear stress now, right? The shear stress now is equal. So the shear stress is equal to tau. Is equal to B over I is always constant. So the rules that we have written before still works. I repeat again, the rules that we have written, remember we have written 5 rules, still apply. Okay. The Q, okay, for this case, the Q is different because thin wall. Now over here, you have to divide by what? 2. Why 2? Because you have 2 Qs. One Q here and the other Q here. You have 2 Q. And then you consider the thickness. Okay, so that is the difference, okay, between thick wall and thin wall analysis. Okay, for thick wall analysis, you do not necessarily construct the shear flow, is it? Right? For thin wall, you have to construct the what? The shear flow. Okay, now let's look at the similarities. Okay, let's look at similarities. So again, I'm going to copy this box. Do we consider the thickness in figure 1 to be horizontal or vertical? Tanmanpreet, are you referring the figure on the left? Yes or no? Can you speak? On the left, okay. So Taranpreet asked, do we consider the thickness in figure 1 to be horizontal or vertical? It is relative to Q. Okay, it's relative to the shear flow Q. So the shear flow is horizontal, right? The thickness is perpendicular. Does that make sense, Taranpreet? I'm still waiting for his response. Yes, good. Okay, you have to be clear on all this. Okay. Right. So now the next thing that we're going to look at is the similarities. What is similar between thin wall and non-thin wall? Okay. So our copy, paste, our I hope to copy and paste again. Okay, so let's look at some similarities now. Okay, so now we want to find the shear stress at point C. We want to find the shear stress at point C. So point C, I don't like to call this neutral axis. This should be addressed as centroid. Okay? Because neutral axis in engineering term means there's no stresses. Centroid is a geometry-based feature. Okay, so now I draw on the right-hand side our centroid. Okay, so this is also our centroid. All right. So now we want to find the shear stress, right? So the area to consider, what we usually do is we divide the area in such a way, okay? We divide the area in this way. We find our Q, right? And then we divide in the other way. This is the other Q that we find. Okay, so that is the area of consideration. Then the thickness is this thickness. Okay, so now our formula is shear stress is equal to V over I, or Vy over Izz is constant. You find our Qz, and then you divide by twice the thickness. Okay, right? Because thickness on the left, thickness on the right. Okay. For this case, for thin wall, okay, for thin wall, you have Q flowing from one side, Q going to the other side. You want to find at point C. Okay. So the area to consider is still very similar, but in smaller size now. So this is the area that we have to consider. Okay. So the formula to use is also shear stress is equal to Vy over Izz Qz. Because it's box beam, right? You take this as